very much for having me here to give this lecture to you on fundamentals of neutron EDM experiments. Maybe a little disclaimer first. I will basically only talk about room temperature neutron EDM experiments with ultra-cold neutrons. So a lot of the concepts also apply to other techniques, but this is the majority of all experiments. So this is what I will focus on. And the idea is that after this lecture, basically every one of you should be able to build their own little EDM experiment in their basement maybe, or wherever you have a suitable environment. So let's see if we can manage that. I'll start with a very, very brief introduction of what we're looking for, which is we're looking for an electric dipole moment of the neutron, which would be CP symmetry violating. And you can see that by looking at the Hamiltonian of such a neutron, here depicted with a magnetic moment and an electric dipole moment in magnetic and electric fields. And if that's the case, if you're in such an environment, then the relevant part of your interaction Hamiltonian looks like this. So you have the coupling to the magnetic field with the magnetic moment and with the electric dipole moment, hypothetic electric dipole moment to the electric field. And now if you let time go backwards, if you apply a time reversal transformation, then you see that some things here flip their sign or their direction if they're vectors, like for example the magnetic field or also the spin. And now if you calculate all these signs correctly, then you end up with a term which is a little bit different than this one here. And so you can see, as those are not the same, this system is obviously not symmetric under time transformation. And from the CPT theorem, we know that if something is violating T symmetry, so time reversal, then it's also violating CP symmetry. So it's so the EDM, the existence of such a non-zero EDM would be a CP symmetry violating quantity, and we want to look for those, and we do that by looking for such a neutron EDM. Now, that's it for the introduction. So let's go for how we measure that. A relatively similar picture here. If we want to measure an EDM, what we do is we again take a neutron, we put it in electric and magnetic field like this, and in this case now the neutron's spin is orthogonal to the magnetic field, and what then happens is, as you probably all know, the neutron will start to precess around the magnetic field. And it does so with a frequency which is proportional to its magnetic moment at the strength of the magnetic field. And now if we assume that there is a little electric dipole moment as well, and let's say it's aligned with the magnetic field like this here, and the electric field is also aligned, then this would also lead to something like a precession motion here. And these two will then actually add up. They go in the same direction, they add up. So your precession frequency will actually increase a little bit here. So you get a higher precession frequency in this case. And now if you invert the electric field and let the magnetic field stay the same, then you still have the same situation for the magnetic field. You still get your precession from the magnetic field, but now the precession due to the electric field and the electric dipole moment points the other way. So this kind of breaks your precession motion. So you get a little bit of a smaller precession frequency here. And now if you combine that and you subtract the two measured frequencies from each other, what you're left with is just a term which has some constants here, the electric field strength and the electric dipole moment that we're interested in. So that's great, because we basically we boil down the whole EDM measurement to measuring a frequency, or rather two frequencies. And according to people like, for example, Arthur Shavlov, that's great because you should never measure anything but frequency. All right. So how do we actually measure such a frequency, such a precession frequency? Also here we are standing on the shoulders of a giant, of Ramsey in this case. This method to measure a precession frequency is called after him, was invented by him, and it basically works like this. We have a holding field, a so-called B0 field pointing upwards in this case, for example. And in this constant B0 holding field, we place a neutron with its spin aligned with the magnetic field, which is the way you would typically start something like this. You would bring the neutrons in with the spins aligned to the magnetic field. And now at a certain time, you irradiate the place where the neutron is with a oscillating B1 field at a certain frequency, which will then flip around the neutron spin by 90 degrees or by pi half. And as soon as the neutron is not aligned with the field anymore, it will start to precess, as we said before. And then for a rather long time here, we just let the neutron precess freely. And then while we're at the same time leaving this B1 frequency running, or the B1 clock if you want. So this keeps running. And then after a certain free precession time, we again do another one of these pi half flips, which is exactly in phase with the first one. We're taking the same part of the oscillating B1 feed here. So we do the same pi half pulse again. And if this oscillating B1 feed here is oscillating at the precession frequency of the neutron in the holding field, then because this is all in phase, we just continue with the second pi half flip where we left off with the first pi half flip. So in total, we will do a full pi flip or a 180-degree flip. And that means that we end up with the neutron being now anti-aligned with the magnetic field. So we now have a spin-down neutron. And if we now look at what happens if we plot the probability to find this neutron here in the spin down, which is on the y-axis here in this spin down state, against the frequency that we use for this oscillating B1 field here, then you can see that you get such an oscillating pattern here. And the reason is basically that if you're not exactly on the right frequency here, and then while the neutron precesses here, it will now precess a little bit, for example, further or less far than if you hit the frequency. And so not all of the neutrons will be exactly in the phase where they get then flipped down to spin down neutrons. So what you can see here is you get, if you're on resonance, if you hit the right frequency, you're down here, you get exactly zero spin ups or zero probability to find the neutron in the spin up state. And once you're a bit off of that, it rises until at some point you are ending up with spin up, 100% spin up probability, and so on. And what you can also see in this plot here is that depending on the free precession time here, you get more or less of these wiggles here in your resonance plot. The reason for that is this, that if you're detuned to some extent from the frequency which would be exactly on resonance here, maybe for example due to an electric dipole moment or something, then what happens is basically that the neutron accumulates some phase here while it's precessing. And if you have now double the precession time here, double the free precession time, then you can accumulate twice as much phase, and thus you get more action here on this plot, more fringes going up and down. And this technique then, to use such a system with a free precession time and two pi half flips, this can then be used to very precisely determine this central point here, which gives you the precession frequency. And this is not a technique which is limited to EDM measurements or something, but this is actually being used in a lot of precision spectroscopy experiments. It's also the basic measurement principle behind a lot of atomic clocks, for example. So this is widely used, and EDM measurements here are just one user of this technique if you want to measure the precession frequency of our neutrons. All right. Now we want to measure these frequencies here, and we want to, from these measured frequencies here, we want to subtract them and then get the electric dipole moment here. And just if you think about this, there's already one very basic realization we can take away from that, and that is this only works, this concept, if our magnetic field in both cases, so here and here, is exactly identical. So in the case where the fields are parallel and the fields are anti-parallel, the magnetic field needs to exactly cancel to zero, such that we are only left here with the term proportional to the electric dipole moment. So that already shows you that in such an experiment, it's extremely important that we control our magnetic field. And what I find extremely interesting is that actually at the moment, the probably two best large magnetic shields, so places where you shield an experiment or a place from the outside magnetic fields, are built or have been built for neutron EDM experiments. So you will see later that we definitely want to have such a shield around our experiment. But let's step one step back, and we need something more than just a good magnetic environment. First of all, we need the neutrons. And for this, let's quickly talk about how they interact. So if you look at a free neutron, the free neutron interacts actually in four significant ways. The first is due to the strong interaction. The neutron experiences a so-called optical or Fermi potential if it approaches a material wall. So not if it approaches a single atom or nucleus, but if it approaches a wall of material, then it sees this Fermi potential. These potentials are typically positive and on the order of about 100 nano electron volts. So very tiny energies, only 100 nano electron volts. Additionally, if you think about the neutron, you know that it has a mass, and so like for all of us, also the neutron experiences gravity, which here on Earth means that the neutron gains or loses approximately 100 nano electron volts if it rises by 1 meter or falls down by 1 meter in the gravity potential of the Earth. That was the second interaction. The third is magnetism. You've already seen that to some extent. The neutron has a spin and a magnetic moment, and thus we can polarize it with strong magnetic fields. And the interaction between the neutron and the magnetic field due to its magnetic moment is approximately 60 nano electron volts per Tesla of field strength. And then there is the fourth interaction, and that is that the free neutron, if it's not bound in a nucleus, is not a stable particle. So it will at some point decay into a proton, an electron, and an antineutrino. And the time scale, the lifetime of the neutron is approximately 15 minutes. So that gives us an idea of how long we have until we have to finish our measurements, because otherwise at some point there will be no neutrons left. Okay, so now if we look at the first three of these interactions here, then you can see that they are all on very similar energy scales. That's all approximately around 100 nano electron volts. And now you can ask the question, what happens if you manage to get a neutron to be so slow and have only a kinetic energy less than, or also on this order of magnitude? And that's what we then call ultra cold neutrons. So neutrons with kinetic energies of less than about 335 nanoelectron volts. And that actually corresponds to only 8 meters per second of velocity, which is a really ridiculously slow velocity for a fundamental particle. And why would we do that? Well, if we have the neutron at this energy, then it basically starts to behave like a ping pong ball, like this ping pong ball here. And we can describe its motion really in a classical way, like this ping pong ball. And the extremely nice thing then is, well, we already know that it reflects from certain materials, and it will now do that under any angle of incidence. So what you can do is you can take a dedicated storage device for ultra-cold neutrons. You can put the neutron in. Oh, it will bounce out, but it will, if the energy is right, it will bounce inside. And you can actually put the lid on top, and the neutron will never get out again. So you can put the neutron to the side, at least for about 15 minutes. And for this time, you can observe the neutron. You can measure, for example, the neutron EDM. And that's why we are so interested in these ultra-cold neutrons. And actually, this my very special neutron box here is not so bad at all. It's a stainless steel cooking pot. So stainless steel is, for example, not a bad material to reflect ultra-cold neutrons. It has a Fermi potential of about 190 nano eV. And as you can see here, the material with the highest Fermi potential that we know of is nickel 58. And that kind of gives you then the definition when we can call a neutron an ultra-cold neutron, because with the nickel 58 cooking pot, if you like, we could store this neutron until it decays after about 50 minutes. But as I said before, most materials actually have a positive Fermi potential. So for example, also aluminum has a much smaller, so only 50 nano eV, but also a positive Fermi potential, which will become important later on. Okay, just a quick word on how we make these neutrons so slow. The way this is typically done is using a super thermal process, which works in a way that you have a cold neutron, which is already relatively slow, but still orders of magnitude faster than the ultra-cold neutrons. And then you put that into some type of crystal lattice that works, for example, with solid deuterium or with superfluid helium. And in there, the neutron can excite phonon vibration and lose basically all of its energy, and be left with just a few nano electron volts of energy. And then it's an ultra-cold neutron. And this phonon here actually will kind of heat up your crystal lattice. So basically, if you want, you can describe this as a two-state system like this here. And if you now cool away the photons, the phonons, sorry, then you can suppress the inverse process of going from the low energies, from the UCN energies to the cold neutron energies by a Boltzmann factor like this. All right, so much for the neutrons. So now we know that if we would want to build ourselves a little EDM experiment, we would have a neutron source, maybe on the left-hand side from where the neutrons come, maybe a hole in the wall or something like this. And we already know that we need a magnetic shield around our main experiment on the other side. And so let's see if we can fill this experiment up a little bit more. So first of all, what we need is, if you think back to how we want to measure the EDM, we need the neutrons polarized. So we need them all with a spin in a well-defined direction. So for example, all will spin up. And there are several ways to do this. One, for example, is with a strong magnetic field. So you've seen before that the magnetic moment is about 60 nano electron volts per Tesla. So if I have, for example, superconducting 5 Tesla magnet, then that produces a spin-dependent potential of about 300 nano electron volts. And it will attract some of the neutrons with this potential, and it will repel others with the same potential. And how does that then look like? So if you have a strong magnetic field here and the neutron approaches from the left-hand side, then it will orient along the direction of the magnetic field and split into two separate states. One is the high field seeking state, where the magnetic moment, here in red, mu, is aligned with the magnetic field. And now here's a first intricacy, if you want. The neutron's magnetic moment is negative, so this actually means that your spin of the neutron is anti-aligned to the magnetic field if the neutron is a high field seeking neutron. So it's a neutron that gets accelerated by the strong magnetic field. If the neutron is oriented the other way around, it gets decelerated by the magnetic field. And if we want to use that for polarization, we can look at the potential energy, if you like. So if your neutron approach is here, and then you have the strong magnet here, it will, for one spin species, so for the high field-seeking neutrons, it will create a potential well of the depth of about 300 nanoelectron volts. And for the low field-seeking neutron state, it will create a potential wall of 300 nano eV height. That means only the neutrons with the spin in this direction, so the magnetic moment aligned with the magnetic field, will be able to traverse this region here. It will actually be accelerated here and then decelerated again back to the velocity they started with behind them, the magnet. If you don't have a superconducting magnet at hand, or you cannot use one in this case, for example, there's also a common alternative. So what you can do is you can use a magnetized iron foil. Also there you have a relatively strong magnetic field, which can be as high as about 2 Tesla or so. And then you have a little bit of a more complicated situation because the iron itself has a Fermi potential of about 210 nanoelectron volts. So you, in general, get a potential wall which is 200 nano eV high, and then depending on the spin state of your neutron, it either gets accelerated or decelerated due to the magnetic field. So you end up with the situation that you have 210 plus or minus, depending on the spin state, 120 nano eV. So then it looks like this in the potential. So the high field seeking neutrons will see a potential wall of about 90 nano eV height, while the low field seeking neutrons will see a wall of 330 nano eV height. So this is how you can make sure that you only get one spin direction of neutrons. And what you then would typically do is, for example, in the beginning, after you have the neutrons coming from your UCN source here, the easiest way to do that is to put up a strong magnet, like for example, a 5 Tesla magnet here, and then afterwards all the neutrons which come through here will have the spin in the same direction. However, that already means that you lose half of your neutrons, because only the neutrons with spin in the right direction are transmitted through your magnet, while the other half is reflected and goes back to your source. Okay, now we have polarized neutrons, polarized ultraquantum neutrons, and now we need to make sure that we keep this polarization. We need to get them to where we want them, where we can use them, and we need to keep them polarized. And for this, what's important is that the so-called adiabaticity coefficient K here, which looks like this, needs to be larger than 1 at all times, much larger than 1, in order for the spins to stay aligned to the magnetic field. You can see what goes in there is the gyromagnetic ratio of the neutron, then the field strength in quadrature, the velocity of the neutron, and the magnetic field change along the direction of travel. And basically what that all boils down to is if your magnetic field changes slow enough, then the spin will always stay aligned with your magnetic field direction. So we can use that to keep the spin in the direction we want. However, we need to be a little bit careful. So in general, what you need to transport ultracold neutrons are, well, typically tubes, for example, which have a very nice surface on the inside, and have a high Fermi potential such that they reflect the neutrons. But also, if you want to transport spin polarized neutrons, the surface of this tube needs to be non-magnetic, because otherwise, once the neutron comes very, very close to the surface before it reflects, it gets a strong magnetic field change or a large magnetic field change, and it might depolarize. So if you look at the options you have, there's, for example, one thing that's used a lot with ultracold neutrons are stainless steel tubes. You can get them very highly polished and electropolished, so relatively good to reflect the neutrons. However, stainless steel is too magnetic to properly transport neutron spins. You can use copper tubes, for example. These are non-magnetic. However, their Fermi potential is lower than for stainless steel. You could also use quartz. That's also relatively good for spin transport, but also with a low Fermi potential. And then what you can also do is you could use glass, which you coat with some layer on the inside, which has nice properties, or you could actually also coat such a layer on the inside of stainless steel tubes, or actually also on copper or quartz, it doesn't matter. So why would you want to do this? Glass tubes are extremely flat. So you can get very, very nice surfaces made from glass. And if you now manage to coat a thin layer of material onto that, which has good transport properties for your neutrons, so a high Fermi potential and being non-magnetic, you can create very smooth tubes which have good neutron reflection properties and good spin properties. So what are your options there? Well, you've seen before that nickel 58 is the best isotope, the best material that we know. Nickel in general is pretty good, has a high Fermi potential. However, you also know that nickel is a ferromagnet. So if we put nickel on the inside of our glass or stainless steel tubes, then the layer is magnetic, and we have the same problem as with the stainless steel tubes themselves. So our neutrons will depolarize. However, what you can do is you can make an alloy, for example, with molybdenum or also with phosphorus, approximately in a weight ratio of 85 to 15. Doesn't need to be exactly that. For example, in phosphorus, you can get away with a little less, but 85-15 works well. And what that does is it lowers the Curie temperature of the material, and if a ferromagnet goes over its Curie temperature, then it gets to be a paramagnet and it's not magnetic anymore. So once you add, for example, the molybdenum here, you end up with a material that is still a very nice reflector for ultra-cold neutrons. You can coat it very smoothly, and it's non-magnetic now. So this works well for spin transport as well. There are other materials you could try to coat onto something, which is diamond or diamond-like carbon, very nice neutron reflection properties and also spin reflection properties. However, there's no process at the moment to coat the inside of a tube, for example, properly with diamond. That is very hard to do. Talking about coating technologies, well, there's several options you have. These nickel coatings, for example, you can apply by sputter coating. Diamond and DLC are CVD and PVD processes. Nickel phosphorus is a chemical process. So there's different options you can use. And then there's also this last one here, which you can use, but it's a little bit complicated. You can coat a flat surface, for example, a glass plate, so that you get the very nice surface quality. And if you then manage to remove the coating and put the coating into any tube, basically, then you would end up with a nice guide as well. However, obviously, that's a relatively delicate process. Okay, so with these options, we can now select the one we like best and build nice neutron guides from them from this, which reflect our neutrons, even if they are spin polarized. However, we also need to make sure that we always have a nice external or a nice magnetic field inside of our tubes. So if we have a big magnet, for example, next to our tube, it could make a very strong or very fast field change in our guide, and we could lose the spin of the neutrons. So we will want to add guiding field coils around our guide, such that there's always a nice and well-defined magnetic field. And that would then look like this. Now, we already said that we want to go, well, let's go back here. We want to go into the inside of our magnetic shield. And right now we are here on the outside. We have our spin polarized neutrons in this guide with the guiding fields around. We need to enter our shield. Now, typically, as in our little toy experiment, the UCNs exit your source horizontally, and also your polarization magnet is typically mounted horizontally and is a very strong magnet by definition. So you have several Tesla of magnetic field. On the other hand, the holding field inside an EDM experiment is normally vertical, and it's typically very small. So we're talking on the order of microtesla here. Additionally, to make things even more complicated, you typically want to be able to change the direction from upwards to downwards of your holding field inside of the experiment, while you would keep your your large polarizer magnet constant typically. Now, that means we need to do some work to get inside our magnetic shield and to move the spin in the right direction. And typically, you would need two sets of coils or currents in those coils in order to slowly adiabatically rotate your spin from forward pointing, for example, to upwards pointing, which means that in the beginning, as in our drawing, you can start with solenoid coils, and then at some point you want to go over to saddle coils, which you could wind on a tube and which would create a vertical field there. There's one more thing to be careful about, again, when we're looking at this adiabaticity, and that is, as you can see, the magnetic field is here in the top, squared even, and the whole expression should be large. So what we need to, at all costs, prevent is a situation where at some point you have no magnetic field at all. Because if you have no magnetic field, this is zero, and then everything else doesn't matter anymore, then your whole K is zero. So we need to be careful not to have zero field at any place in our neutron guide. And this now gets a little complicated because the shielding material you use for these magnetic shields has a high magnetic permeability mu, which in principle means something like it attracts magnetic field lines very well. It sucks the field lines into its material. So if you pass with your guide through this shield layers, you need to be very careful that your field lines don't get bent out of shape by the shield, and you end up with a little field zero at some point, which would then kill all of your polarization. So this needs to be included in your calculations of how you need to make your coils to transport the spin to the inside of your magnetically shielded room. And we've already seen that, for example, for the Los Alamos experiment on Monday in the talk by Tim Chubb. So you can see that a lot of thought has gone into making such complicated coils such that you can transport your spin and rotate the spin at the same time through your magnetic shield layers. All right, so we put that here. I will not draw this correctly. I will just put some solenoidal coils here, but these are a little bit more complicated. Okay, in addition, already here, I drew it, and it's clear that on the inside of your shield, you want to have the coils which then produce your holding field, your B0 field. And these need to be, you want them to be large because they should make a very homogeneous field, which is everywhere the same. And you need a very, very stable magnetic, very stable power supply to drive a current through these coils to get a very, very stable magnetic field there, because otherwise, all your effort to have a nice magnetic shield would be moot if you have a very much varying current in those coils here, because then again you would get very different B0 fields. Now, what do we want to do inside that? Well, we have our shield, we have our magnetic our holding field or B0 field, and now we get to the heart of the matter. We need a chamber where we can put the neutrons in, and then basically do Ramsey's technique to measure the frequency, the precession frequency, in the presence of the B0 magnetic field that we already talked about and strong electric fields. So in order to do that, what you want to have is, in principle, a precession chamber like this one here, where you would have a top and a bottom plate here and here from a conductive material as your electrodes. And then you need a sidewall, which, if you do it symmetrically, is typically a ring here, from some insulating material, which first of all supports the whole assembly, and then also makes sure that your neutrons cannot exit here between the electrodes. This has some requirements. So first of all, you want these electrodes here to be very, very parallel, because if they are not parallel, then you get, if they are tilted to some extent, then your electric field will not be the same everywhere in your chamber, and that makes everything more complicated. As you see in the schematics, what we want is a homogeneous magnetic field and a homogeneous electric field, and then things are simple. Additionally, to being parallel, the whole chamber here, so both electrodes plus the ring, need to be very well aligned with the magnetic field. Again, for the same reason, what you want is to measure in the field's parallel case and in the field's anti-parallel case, so you don't want any angles in between there. That's first of all inefficient, and second of all makes for a lot of headaches when it comes to systematic effects. You want to apply a very high electric field between these two plates here. We're talking about hundreds of kilovolts there. And that means that all of these plates here, you cannot really have sharp edges or something. Everything has to be smooth and rounded. You need to do a lot of simulations there to get an electric field friendly shape in order to get that as high as possible. Then, as with the guides before, it's clear that we want all of these walls that the neutrons can see. We want all of this from a very low neutron loss and also spin loss material. So again, you need a material which you, for example, coat. You can, you can not use conductive materials on the ring here, because otherwise you couldn't apply a magnetic field anymore, electric field anymore. Sorry. So you need to take care that this is well coated with a good material or made from a good base material from the start. It also needs to be, the materials you use need to be extremely non-magnetic here, because again, it's the same reason as that that everything there has to be aligned correctly and so on. If you have magnetic pieces in here, the field lines, the magnetic field lines in the chamber will not be parallel anymore, but you will get complicated fields, and this is not good for your measurement at all. All of this actually applies not only to the chamber itself, but somehow you need to close this hole where you fill the neutrons in after they are in. So also your typically movable device here, your shutter or so, needs to be compatible with high voltage in this chamber. It needs to be coated with a nice material and so on. And then you typically need a window for light access that depends on how you build your experiment. For example, here the window would be in the ring. We have also already seen some talks where such windows are in the electrodes. We get to that in a second. And so one solution, for example, there are several solutions, but one solution to build such a precession chamber would be, for example, using diamond-like carbon on aluminum electrodes. I said before, you cannot coat the inside of tubes with diamond-like carbon, but you can coat large plates, and you can very precisely machine aluminum. So you can get very parallel electrodes there. You coat them with DLC, and then they have a high Fermi potential and reflect neutrons and spins very nicely. And for this ring here, one option is, for example, to use deuterated polystyrene on a polystyrene ring. Polystyrene is relatively good to insulate between these plates at high voltage. However, you cannot just use polystyrene for your ring, because polystyrene, or actually all polymers, are full of hydrogen atoms. And if an ultra-cold neutron scatters off a room temperature hydrogen atom, it will gain energy, and then you will not be able to store it no longer. So what you have to do is you replace the hydrogen atoms in your polystyrene with deuterated with deuterons. So sorry, not with deuterons, but with deuterium. It's a full atom, and then you coat that on the inside of your ring, because it only matters in the innermost layer. Okay. Now, so this is one option. There are different options how to build such a chamber. Now let's briefly talk about this hole here. So why do we want to have a hole for light access in our precession chamber or in our electrodes? The reason is we can use the feature that, for example, mercury 199, the isotope 199 of mercury, offers us that it has a spin-dependent light absorption. These for light at the right wavelength. If you shine circularly polarized light onto mercury atoms, then depending on if the spin of the mercury atom points towards where the light is coming from or in the same direction, you get different light transmission or light absorption there. So if you put a photodetector on the other side, you shine in the light here from the top, put a photodetector on the bottom, then like this, you see that you get very little light through your chamber full of mercury atoms when the spins are when the spin points against the light direction, and you get a lot of light if it points in the same direction, and something in the middle if the spin is orthogonal. So like this, you can measure the spin direction of the mercury atoms. And if you have now these mercury atoms also precessing just like the neutrons do, then you will actually be able to read out the spin precession live on a photodetector if you shine light on it, and that then looks like this. This is the signal on your photodetector for a light beam shining through such an EDM cell. And at some point you fill in mercury gas here, then you do a spin flip to get just with like the neutrons, to get the spins orthogonal to the magnetic field. And then they will precess, and you can see this on your photomultiplier signal. So here's a zoom, you see this is nicely sinusoidal, and the shape, the envelope decays a little bit over time. And you can do this for very long times. Here is plotted for something like 30 seconds or so of precession time. And like this, you can live measure the precession frequency of the mercury atoms. And as we know that mercury does not have an EDM, we can use this to get a live measure of the magnetic field inside of our EDM chamber, or if you have something like this in the electrode or so, then very close to the chamber. And why do you need this? Well, if you look at the precession frequency of your neutrons over time, in this case here over a relatively long time, so every cycle here is 5 minutes long, then even if you have a very nice magnetic shield around and you took great care, this will likely still drift or maybe jump to some extent. So you can see here that the frequency gets bigger over time, then it gets smaller again, and then here there's even a big jump. So like this, interpreting this frequency is going to be hard. However, if you have such a mercury magnetometer nearby or in the same volume actually, then what you can do is you can use the frequency with which the mercury atoms precess, this FHG here, to normalize your neutron precession frequency. And what you see is that you get basically a horizontal line here, which is very nice and now a very good signal to analyze, for example, for changes of the frequency when you apply electric field. Okay, so we put this into our toy experiment here. We also add a vacuum tank because I guess it's obvious you need your neutrons in vacuum such that they don't interact with your air. We put in electrodes, we put in the precession chamber, and the further details are not really shown here, but that doesn't matter. You know them by now. Now, we have talked a lot about these spin flips. And for now, I've always only said, well, we flip the spin by pi half, and then we do some measurements or so. So how does that actually work? How do you flip a neutron or also a mercury spin by, for example, an angle of pi half? Let's again start in the system or in the situation where we have a holding field B0, static, very constant homogeneous field, and you have the spin-aligned neutron sitting in that holding field. If it's aligned with the magnetic field, there is no precession. The neutron will just point along the field. Now, we can irradiate a second field, again using coils, and then driving the coils in such a way with electric currents that we get a time-dependent B1 field. And we can make it so that this B1 field rotates around the B0 field. And as soon as we start doing this, basically, you can already see that now the neutron sees a combined field of these two. So it will not be fully aligned with the magnetic field anymore, and it will start to precess. Now, if we choose the B1 frequency, so the frequency with which this field rotates, to be precisely the precession frequency of the neutron in the holding field, in the B0 field, then what we can do is, because this system here is way too complicated for us to understand what's going on, we can transform into a coordinate system which also rotates at the same frequency. And if we go into this rotating frame, you see that, well, now in this frame, the neutron doesn't rotate around the B0 field anymore because we are rotating at the same angular velocity. And what's left is now the B1 field, which is now not time dependent anymore because we are rotating at the same frequency also as the B1 field. So now the B1 field is a static field orthogonal to our spin direction now, our initial spin direction here. And what will happen now in this frame is, again, like said before, now we have a neutron with a spin orthogonal to a magnetic field. And now the neutron will precess around this magnetic field. And so it will kind of rotate orthogonal to the plane of your screen now, and flip around at this frequency here, which is now only proportionate to the direct magnetic ratio of the neutron and the magnitude of the B1 field that we irradiate. And like this, if we now stop the B1 field at some time, we can get the spin to rotate by a certain phase there, which is just the rotation frequency omega r times the time that we have this, that we apply this spin flip pulse. And if we then put this expression here for the frequency in there, you see that the phase by which you turn the neutron spin is just gamma times the magnitude of your applied B1 field times the time that you irradiate this, or that you irradiate this oscillating or rotating field there. And like this, if you now tune the magnitude of your B1 field, the amplitude of your B1 field, and the time that you do this, you can basically freely choose any given angle by which you want to rotate your neutron. And after that, your neutron is at this angle to the B0 field again, if we get out of the rotating frame again. And you have, for example, if you put in the correct magnitude and time, you have a nicely 90 degrees or pi half flipped neutron or Mercury, which then again will start to precess around the holding field. So for this, again, here we put in some coils here to be able to do this spin flip. Also there we need large coils because we know that we have the the same or the co-aligned spins everywhere in our precession chamber. And now we want also this B1 field that we irradiate to be very homogeneous in there, such that all spins, all neutrons inside the chamber, be it on the right-hand side or on the left-hand side, they should see the same amplitude for the same time, such that they all flip exactly by 90 degrees. Okay, so now we have all the components together to do this Ramsey method to determine the precession frequency. And yeah, we can do this now. We fill polarized neutrons in as spin up, we do the spin flips, we wait, we do another spin flip, and then we are left with, for example, spin down neutrons or something in between if we are not exactly on resonance here. So what do we do now? How do we figure that out? We need to somehow measure how many of the neutrons are spin up and how many are spin down here. And the first thing we have to do is we have to get out of our chamber again. And unfortunately, we only have typically one tube going into our chamber, so we need to go back in the same way we came in. However, we need to take care that we don't end up back in our polarization magnet or in our UCN source. So we need some type of switch. And what I show you here are two UCN switches which have been built. One is from the neutron EDM experiment at PSI. One is from the pan EDM experiment at DRLL. You see they look roughly similar. And what you have to do there in order to reroute the neutron's direction is basically you rotate, or it doesn't have to be round, but you move guide pieces into a certain gap between two guides, which then either, for example, here are a tube straight through. So if the neutrons come in up here, they go straight through, or you put in bent pieces like these, which rotate which guide the beam by 90 degrees. You can also see this here. This one goes through, you can see through it. And this one, for example, goes from the back to the side here. And there you already obviously see that this is complicated to build these things in a good way, because in order to be able to move your guides, you obviously need some degrees of freedom, some gaps. Um, and on the other hand, if you have a gap between the two tubes, which connect in order to guide your neutrons, then you will immediately lose some of your neutrons. So you need to have a very good compromise here on very, very small gaps, but still your device needs to be movable in order to switch one guide piece to the other. And then you would typically, once the neutrons are back out of your precession chamber, you would, for example, change or switch their route to go downwards, for example. And also there, and also in this switch itself, which is not really drawn here, you need again to be sure that you keep a holding field everywhere in place for your spins, because we want to measure on the outside um, how the polarization of your neutrons is, and so we need to preserve it until we measured it. Okay, now we have the neutrons, including their precession, their polarization. We have them out of our shield again. That's nice, but we still have to measure them somehow. And so the first thing we have to figure out is how do we even measure them at all? We have the ultra neutrons, which are obviously electrically neutral particles with very, very little energy, only a few nanoelectron volts. And what we want to have is some type of an electric signal in order to digitize that, in order to record how many neutrons we counted. And you can see immediately that this will not easily work. You cannot really easily create an electric signal from a low energy neutral particle. That's very hard. So we need some type of trick. And the trick that we use, and we are lucky that nature provides us with some of them, is we can use some material which can absorb the neutron and then immediately decay afterwards. And in order to choose such a material, we can look into some tables. So this is a table of the materials with the largest absorption cross-section for neutrons here. It's a list you can, for example, find at the LL. And you see in red highlighted are some materials which are useful for neutron research. And for the purpose of absorbing and then decaying and being able to count the neutrons, the most interesting are helium-3 here, boron-10, and lithium-6. And how does that work? Well, if for example, a helium-3 atom captures a neutron, then it will immediately decay into a triton, a proton, and the two will fly apart with some energy. The same basically for lithium-6, you get out an alpha and a triton, and for boron-10, you get lithium and helium, an alpha particle. And typically, the products of this, they will fly back to back away from each other. And that means that it's relatively easy then to just put a regular charge particle detector behind your material, which absorbs the neutrons and decays. And so, for example, you can use gas ionization detectors. You can use scintillation light, or scintillators, where a charged particle traversing through creates light, which you can then measure with, for example, a photomultiplier tube or a silicon photomultiplier. You can also use silicon detectors like CCDs or something, as long as you have some material in front of that which creates charged particles from the neutrons. And so the obvious choice, if you have a gas detector, for example, could be helium-3. Helium-3 is a gas as well, so you could just mix a little bit of helium-3 into your ionization detector, and that immediately makes your otherwise not neutron sensitive detector neutron sensitive. For lithium, this is typically doped into scintillators, because lithium by itself is a relatively volatile material, so you cannot use metallic lithium. And boron-10, for example, is a relatively well-behaved material, so you can use just a few nanometer layer of boron-10, for example, on a silicon detector, or also on any of the others. So like this, we have a way to measure our neutrons. However, there's one more thing that we have to take into account, And that is, as I said before, that most materials actually have a positive Fermi potential. So for example, a typical neutron detector using helium-3, especially if it's made for normally higher energy neutrons, any gas detector will need an entrance window to some extent. And so, for example, an aluminum entrance window would be very typical for a neutron detector. However, if you have an ultra-cold neutron detector with an aluminum entrance window, that means that all the neutrons below 50 nanoelectron volts of kinetic energy, they will never traverse this entrance window. And so you need to make sure that that your neutrons all have the right energy to even get into the active volume of your detector. So we put a detector below our toy experiment here. And now, at least finally, we have a way to count the neutrons which come out of our precession chamber. However, we don't only want to count them, we also want to know their spin. And typically, these detection techniques are spin independent. So you would normally just get you get an electric signal for every neutron that's counted, but you have no idea with which spin it was detected. So the only way we can do that is we have to make sure that we know that only one spin state of the neutron even arrives at our detector for a certain time. And then we know that, or like this, we can then detect the amount of, for example, spin up neutrons or spin down neutrons. How do we do this? Well, basically, we just use another spin polarizer like you've seen before. We now call it analyzer, but it's exactly the same thing. So for example, going back to the idea of the magnetized iron foil, if we have high field seeking, or if we want to measure the high field seeking neutron state here, then we just put an iron foil with a magnetic field in front of our detector. And like this, these neutrons get attracted and go through this blue region here. Basically, they only see a small potential wall of 90 nano eV, while the other spins, or the neutrons with the other spin direction, they will see a large potential wall, and they will not traverse into your detector, so they will not be counted. And here you can see something which you can now combine. We said that some detectors might have a Fermi potential, so you need a certain minimum energy. Also, these iron foil polarizers or analyzers, they still have this 90 nano eV potential wall. So what you can, for example, do is you can just let your neutrons free fall for about 90 centimeters. Then you put your magnetized iron foil. The neutrons will get through that because they just gained 90 nanoelectron volts. And then if you put a detector after that, which has less than 90 nano eV of Fermi potential at the window, then your neutrons will also get in there. Okay, so we can also put this in place. And now we can measure the spin, or we can count the number of neutrons which arrive here with this spin state. So that's already pretty good, but it's not 100% all what we need, because as I said before, from Ramsey's measurement technique here, we get we want to measure how many spin up neutrons and how many spin down neutrons we have. We don't want only one component, so we need the other as well. And so we need to do something more. In order to get through this spin analyzer here, the neutrons have to have the right spin state. Now, if you want to measure the other spin state, well, we could think of doing just another spin flip like we did it before in the chamber, just now not by 90 degrees, but by 180 degrees. Like this, we would switch to the different spin state, and we could have the neutrons, the other spin state of the neutrons, traverse through the analyzer. However, we need to think about the situation here. In contrast to before, now the neutrons empty from our chambers towards our detectors for a very long time. So they're not there all at the same time. Also, their velocities vary by some meters per second. So some of them might travel with 2 meters per second, some with 3 meters per second or so. So very different velocities. And also their trajectories will be mixed. So they bounce around the walls. So you don't really know how they fly. And in the precession chamber, we had the situation that we had all of the neutrons in a confined volume, and we were able to to irradiate a homogeneous rotating field into the whole chamber at the same time. And then we could use the strength of the field and the time of the pulse in order to set the right angle. So obviously this doesn't work for our guide towards the detector. But luckily there's another way to do that. And we will look at this now. What you need to prepare before you can do such a spin flip is a little bit of a different field situation. And that is, now you need a gradient in your holding field. So the red line here is your spin holding field or spin guiding field in the guide towards the detector. Let's say the neutron flies in positive z direction, so from here to here. It will fly through such a magnetic field gradient. So its spin in principle will be aligned with that. And then we choose a position in this magnetic field gradient where the magnetic field then corresponds to the BASF here. We choose that for the location of the center of our spin flipper. And now again, we do the same thing as before. We irradiate a rotating magnetic field, which is orthogonal and rotates around your holding field here. And for the frequency of rotation, we choose the frequency which corresponds to the Lama frequency of the neutrons at the magnetic field here at the position where we choose the center of our spin flipper. So that's the expression for the frequency. So again, we have this rotating frame, and again we do the same trick as before. We transform into this co-rotating frame, which I now indicate here as x prime and z prime. The B1 prime field is now constant along, for example, the x prime direction, and the B0 prime or the B0 field in the z prime direction is still the same as before. Now, if we think about this, we have seen before that if your system rotates at the same frequency as the neutrons would precess, to the neutrons, it seems like this cancels the holding field, and you don't have to consider this for spin precession matters. So the same thing happens here as well. However, if we start here, for example, our neutron up here is still in a higher field than the field we chose here to choose the precession frequency. Sorry, the spin flip frequency. So the B0 will not be completely compensated, but there will just be a term proportional to the this spin flipper frequency, which gives you something like a change in magnetic field that you effectively see in the rotating frame now. And so if you include the B1 here, you get an effective field which looks like this and has a certain angle here. Again, this picture is for some place here in front where your magnetic field is still stronger than the magnetic field at the spin flipper center. Now, if you consider this, and now you let the neutron traverse your spin flipper from the left to the right, and you start here with a high field seeking state, so your spin is anti-aligned with the holding field. Then what happens once you enter your spin flipper? The shaded region here is kind of indicating the extent of your spin flipper coil. So as soon as you enter this coil, the neutron starts to see the B1 field as a static field along the x prime direction. And so the effective field it sees will get this angle here, will get tilted a bit. And then the closer your neutron comes to the point where the spin flipper frequency corresponds to the Lama frequency of the neutron in that field, the less of an effective B0 field the neutron will see here, and correspondingly the larger your angle theta here gets, and the more your effective field in this rotating frame will be tilted out of the forward region. Then in the center here at the position of your spin flipper, you're in the same situation as before in the precession chamber. So now the the field in the rotating frame is exactly orthogonal to your B0 holding field in the outside. And then if you go on, now your precession frequency or your llama frequency in lower fields is now smaller than the spin flipper frequency. So this just goes on here, and now you have an effective B0, well, kind of holding field or a virtual holding field, actually pointing backwards here. And now if you exit the spin flipper here at the end, you can now see that while this effective field now points backwards, well, your actual B0 field still points the same way as before. And now you have a neutron with its spin aligned with the holding field. And so now this is a low field seeking neutron. It has been flipped by 180 degrees, and it's a different spin state. So by doing this, and if you make sure that your magnetic field gradient that you prepare in the beginning and the amplitude here of your B1 field, if this is all chosen in a way that this tilting of the effective field out of the forward direction and then to orthogonal and backwards is a slow movement of the spin, kind of an adiabatic move of the field, then your spin will follow that field. And thus you have built an adiabatic spin flipper, which is independent of the velocity of the neutron. So if the neutron at any velocity starts up here as a high field seeker, it traverses to this side, it will get out here as a low field seeking neutron. And that is something now which we can very well put into the neutron guide before our detector. And actually, if we, for example, use this technique with an iron foil and a magnet which polarizes the iron foil, then we already also have a magnetic field there, which in a certain voltage, depending on the distance to the foil, will have a magnetic field gradient. So if we match that all well, then we can relatively easily build our spin flipper right above the spin analyzer here. And like this now, we can choose which spin state of the neutrons we allow through and count in our detector. And then if we switch on or off the spin flipper coil, we allow the other spin component to traverse the spin analyzer, and always the other component is just stored above the analyzer foil, so that just stays up there and bounces on the foil and basically waits for you to measure it later. And well, as you can see now, like this, we now have a complete toy neutron EDM experiment where we go from a UCN source through a polarizer, guiding field coils into our magnetic shield, where we have a precession chamber with magnetic and electric fields. We do Ramsey's technique there to measure the frequency, and then we guide the neutrons out again and detect their spins in the UCN detector. So in principle, with this, you can now go and build your own EDM experiment. However, it's clear that if you want to do that with a very high precision, that you need to optimize a lot of things, and some things might be a little more complicated than shown here. So if you look at new projects nowadays, building new EDM experiments, for example, you can see that they all use double chambers, which means you don't have one precession chamber where you have the neutrons inside, but now you use two chambers typically on top of each other if the magnetic field goes from top to bottom or from bottom to top. And that has one very nice feature. Your magnetic field goes through both chambers. So that's, say, always in one direction. But due to the fact that you keep the outer two electrodes on ground potential and charge the inner electrode to plus or minus, so let's say, for example, 200 kilovolts, your electric field in one chamber will be opposite to the one in the other chamber. So at the same time, you measure the precession frequency with parallel and anti-parallel fields, which is great because then you get rid of first order magnetic field drifts. However, now if your magnetic field would drift a little more in the top part of your chamber than in the bottom, you could still get wrong results. So you still need to make sure that you're in a good magnetic situation. Additionally, the fact that you have the high voltage here in the center sandwiched by two electrodes on ground potential, is also makes it easier to reach very high voltages there, because you have to imagine that your vacuum tank is somewhere around this chamber, and at some point probably your vacuum tank will be on ground potential, and that means that you have some points where the high voltage is then closer to the grounded vacuum tank, for example, and that can be then difficult to create a very high electric field. Additionally, also for all instrumentation that you want to put up on the electrodes, say on below and above the chamber, it's much easier if this is on ground potential than on several hundred kilovolts. So that's one feature that modern experiments all have. Another one is the way you detect your spins. You have seen that with one spin flipper and one detector, you can measure one after the other the different spin states. However, if you now go and put two detectors and two spin flippers and two analyzers next to each other, then you can basically measure the spin up and spin down neutrons side by side. So one of them is detected here, for example, on the left-hand side, one is detected on the right-hand side. And you don't need to store the wrong spin component neutrons for such a long time. And that's good, because during the storage time of this spin component, which you're currently not measuring, some of the neutrons decay, some might depolarize, you might lose them somehow. So this is more efficient and also systematically more clean. It turns out that if you need two chambers, or if you have two chambers, then you actually need four detectors. So you will put two of these simultaneous spin analyzer detectors next to each other. And you see that things are getting more and more complicated. Then what's next? Magnetometry. In the toy experiment we built, we just had the neutrons and the mercury processing, and we used that for our experiment. However, if you have more places where you measure your magnetic field, then obviously you learn much more about the shape of your magnetic field. And so if you look, for example, at the currently upcoming experiments, like this is a sketch of pan EDM or N2 EDM here, you see that there are several additional magnetometers here and here and here, and all these little bubbles around the N2 EDM experiment. All of these are magnetic field sensors, and with this you reconstruct the exact shape in the shape of the magnetic field in your chamber, in order to, for example, see such gradient changes if the field at the top of the chamber changes a little bit different from the bottom chamber or so, for example. And then there are many more details you need to take care of, mainly in order to avoid systematic effects on your measurement. So, for example, either your magnetic field or also your devices may drift a little bit, and so you could get effects on your measurement which evolve with time. And in order to get rid of this, what you can do is you just sprinkle some more adiabatic fast passage spin flippers all over your neutron guides, and you do your experiment in various different situations. So, for example, you change the direction of your E0 holding field in your chamber, or you change the initial spin of the neutrons with which they enter your experiment. You can do this by just putting one of these spin flippers right behind your polarizing magnet, for example. You also change the electric field direction regularly. So sometimes you measure with the electric field pointing, or in the case of a double chamber experiment, with the electrode on negative high voltage, sometimes on positive high voltage. All of this shouldn't change the EDM result because it's symmetric, but you need to do this to make sure that no effects because of some asymmetry somewhere change your result and mimic a wrong signal. Then, for example, also you're charging your electrodes to a very high voltage, which means there's some current flowing there. And if you have a current flowing, then that creates a magnetic field. Now, if you have a high voltage during your measurement, and you have a tiny little leakage current from the positive electrode to the negative electrode, or one of the negative electrodes, for example, or ground electrodes, then this also creates a magnetic field in some way or shape. And that's unfortunately even then correlated to the direction of your electric field, which is horrible because it looks like an EDM signal in your final data analysis. So what you can do is you can very precisely measure this leakage current, or if there's a leakage current between your electrodes. However, it's something where you, for example, have to be very careful that you get the return paths right. So if you do a leakage current measurement in a bad way, you can actually create dangerous fields in your chamber for your measurements. So you need to be very careful there. And one recent development, for example, is that you can use a leakage current measurement device in your high voltage electrode. So on high voltage, for example, at 200 kilovolts or so, which, for example, you can power with the laser from the outside and through a solar cell. So you don't need any cable connections to that or something like this. Then also additionally, while you have your very nice magnetically shielded room and B0 coils, in order to first of all make sure that you really don't have gradients in your chamber, you will need a set of more coils around your chamber. But you could also apply some well-defined gradients by well, yeah, you can apply them explicitly in order to see how your measurement changes if you really apply such a gradient. And so you will need a large array of additional so-called trim coils in addition to your B0 coil. So you see many little details to make your measurements better and more systematically clean. Also enter into modern such experiments. Now, very briefly about systematic effects. I just told you that you build your experiment, or you operate your experiment in a way to avoid such systematic effects, but you will not be able to get rid of all of them. And just to give you an idea, this is a list of systematic effects from the latest limit on the EDM. And I'm just picking out one of them to show you what interesting effects can play a role, and that's this delta Earth term here, which is actually a thing if you look at the neutron, or if you compare the neutron precession frequency and the mercury precession frequency, and due to the fact that they have different gyromagnetic ratios, and one is negative and one is positive, you suddenly get an effect due to the fact that your experiment sits on our planet Earth. It measures for 5 minutes or so, and in these 5 minutes, the Earth rotates under your experiment, like under a Foucault pendule, for example. And so this R ratio between the precession frequency of the neutrons and the mercury atoms suddenly starts to depend on the direction of your holding field, and you need to correct for this in your data analysis. Luckily, in this case, we know the Earth rotation relatively well, so this is something you can control. And there's much more systematic effects here, which might play a role. And that brings me to basically almost the end, and that is, if you build an EDM experiment now, you're looking back on a long history of neutron EDM measurements. You want to have very high precision. You're building very good apparatuses in order to measure at the highest possible precision. And that also means that you have to consider many systematic effects, like, for example, the Earth rotation, but many more. And it turns out that, well, all experiments up to now have measured no neutron electric dipole moment, so zero, or something compatible with zero within error bars. So if you're analyzing many systematic effects and you have an idea what to expect, so zero, for example, then the only real way out of this problem is that you do a blind analysis, which means that you do all of your analysis before you know the final result. Because otherwise you could stop looking for new systematic effects once you're at zero. Or if you're not at zero, you could try very hard to find another systematic effect to get you back to zero. So you need to somehow change what result you will get during your analysis work, and only at the very end, when all of your analysis is finished, need to look at the real example. And in some experiments that's simple, but in an EDM experiment, what you're basically doing is you're comparing a lot of clocks. So you've seen we have the precessing neutrons, we might have the precessing mercury, we have different magnetometers, which are also basically clocks or rotating spins or something like this. And so it's very, very hard to change one of these parameters without the others noticing or making it obvious. Because if you have a very obvious blinding, like for example, you change one of the frequencies that we have, then you will see a difference with respect to the other frequencies in your experiment, and you immediately can see the blinding offset. So what you have to do in order to do this without having issues with these clocks, or at least one way to do it is you can fake a different precession frequency by shifting some of your neutrons, which you count as spin ups, to spin downs, for example. So what you typically do is you measure at 4 points around the central central resonance frequency here. And now by saying a few of the spin down neutrons here, we add them to the spin ups, and we take some away on the right hand side. We put some, well, so we put some spin downs to spin ups on the left hand side, some spin ups to spin downs on the right hand side. We will lower the counts here on the right hand side. We will increase the counts on the left hand side, and like this, we shift the whole precession frequency, or the measurement of the precession frequency, a bit to the left. And so in order to do this, you need to basically do an online analysis when you count your neutrons and assign which neutron has which spin state. But if you do that, you can change your frequency like this without touching any of the other frequencies. And that's a very nice way to blind such an experiment, and to be sure then later on that you analyze all your systematic effects without aiming for zero, and thus making mistakes. Okay, and that brings me to my summary already. I hope I could convince you that neutron EDM experiments are not rocket science. However, if you want to do it very precisely, then there's obviously a lot of important details you have to take care about. And you've seen a lot of talks already on such experiments being built right now. There will still be some upcoming. It's a great time to do neutron EDM measurements at the moment. Many new experiments are upcoming, and neutron EDM measurements have a bright future ahead. And so it's great to be here on this workshop and see all the developments there. And with that, I'd like to thank you all for your attention.
Thank you. Thank you very much, Dieter. Now we have plenty of time for questions and discussion. So you can raise your hand. Okay, Skyler, I see you have your hand raised.
Yes, I'll just start while other people are reflecting. Thank you, Dieter, for that very pedagogical presentation. That was really nice. I just wanted to make a small comment on your early introduction to the neutron potentials of different materials. So nickel 58 is great, but if you look at other isotopes, you actually find things such as dysprosium 164 that have really phenomenal potential. So that one is over a micro EV. Even the cost is that it also appears on your list of strong neutron absorbers. And so you have always to worry about this compromise between the real part of the potential and the imaginary part.
Yes, yes.
You take the one which is corresponding to your neutron spectrum and so forth.
Okay, now we can take the question by Pierre.
Yes, so it was a very nice talk. Thanks a lot for all these details. So for me, who is a bit outside of this community, it was particularly enlightening. So I had a question because I'm missing a bit the orders of magnitude concerning the transport efficiencies. So you say that an ultra-cold neutron is something which has less than 300 about nano EV. So we've seen Fermi potentials for materials which are much below sometimes than this. What are typical efficiencies, and do they? Of course, they will matter, I guess.
You mean for transporting them or for production of the ultra-cold neutrons?
Well, I was thinking about transporting them first, but as you pointed out, yes, it would be also interesting to know how much you catch from a spallation facility or reactors, but that's
yeah. So
question.
Production is extremely inefficient, unfortunately. So I mean, you know that typical say cold neutron sources, you can get extremely large fluxes of cold neutrons, for example. And ultra cold neutron production is intrinsically very inefficient. So typically the numbers, let's start from the back then. No, let's not start from the back. So you can typically create a few million UCNs per 5-minute shot or so from a good UCN source. Now this is then say from 0 to maybe 335 nano eV or something. Then you need to transport the neutrons into your experiment. And now immediately you will see that you get a certain kind of energy acceptance for your device, which is to first order the material with the lowest Fermi potential in your system, which often, for example, for EDM experiments is the wall coating or the walls of these insulating rings here. With nickel or diamond on metal, we have very high potentials, but getting something which is isolating is not very simple. So typically that gives you the upper bound of your energy acceptance. And then, well, transport efficiency after you polarize, which reduces your transmission by a factor of 2, can be relatively good because you have your neutrons in principle do total reflections on your guides, and you have a little bit of a loss per wall collision, which with good materials you can get to the 10 to the minus 5 or so range, low 10 to the minus 4 range. So you only lose a neutron if it touches the wall more than, say, 10,000 times on average. However, then you not only have the transport is relatively fast and not so many bounces. You go through a few meters of guides into your chamber, but then the neutrons will stay inside your chambers here or here, and you want to have them stay there as long as possible. So again, also in your chamber, you have these loss probability per wall collision. And you also have then, if you have storage for a long time, so you have beta decay at some point. And that means that you have to kind of tune your overall loss probability together with all the other parameters that you have in your system to go for your system, for your setup to the optimum point in storage time to get the best result out of your experiment in the end. So transport is not the dominating effect for any EDM, because you store for a long time, and the longer you store, the more neutrons you lose. And so you have to optimize the time, how long you store them, such that you're still statistically significant in the end.
Okay, so I understand that it's more a storage time problem than transport one. But then what is the typical storage time you can reach? Is this hundreds of seconds you were speaking about? Or?
So in the past, typically up to, say, 3 minutes or so, 180 seconds were used. Well, this depends a little bit. It depends on your neutron spectrum, for example. It depends on your materials. It depends on how many initial neutrons you have in the beginning. In the end, all the experiments up to now are statistics limited, but you can basically you just have to calculate your statistical sensitivity with all your parameters for your given experiment and your source, your energy spectrum, and then you optimize that for the best time. But typically something around 180, 200 seconds or so up to now.
Thanks a lot.
I don't see any more questions. Oh, maybe concerning Pierre's question, we can quote the number of detected neutrons in the PSI experiment compared to So the door produce UCNs, right?
Yeah, so as I said, you have a few million UCNs in total produced at such a source, or at the PSI source in this case, per shot. And in the end, the average detected number of neutrons was on the order of 20,000, if I remember correctly.
Yes.
So after polarization, after transport, after storage for 3 minutes, after transport back out, and including detection efficiency and so on, you were down to something 20,000 per 5-minute shot. And then you repeat and repeat and repeat. I think we did 60,000 repetitions for the NEDM result.
So it's 1% or so.
Yeah, I mean, it's hard to say because your typical output of the sources is a different energy spectrum. So
Sure.
You go to a certain height that changes your energy spectrum again. Yeah,
But I think this is typical for all of the sources that are being foreseen for EDM experiments at the moment. You lose a couple orders of magnitude between UCN production and measurement at the end of an EDM cycle.
Yeah,
it's one of the major challenges in the field.
Yeah, I've seen Florian's hand raised briefly, but one. Yeah, Florian.
Yes. Sorry. Yeah, hi, Dieter. Nice talk, as usual. I have a question, more like, I had a thought recently, and I just want to see what you say about this. So in the most EDM experiments, the B0 field is about 1 microtesla or something about that. If we could flip the neutron spin nevertheless, would it make sense to make it measure something like 0 field, actually, really 0 field? I mean, just very speculative question.
Well, I would say if you compare something like a signal to noise, so how much precession phase per time you get from the electric field with respect to the magnetic field, then yes, you would probably gain from that. But as far as I understand it, you run into major problems, for example, with magnetometry, if you go to very low fields. But I mean, from very much from the principles, I think you would gain if you have a larger signal from the electric field, relatively speaking, to the precession from the magnetic field. Yes.
I mean, because there's very precise magnetometers at 0 field as well, right? So, I mean, I'm not speaking about 0, but maybe 1 nanotesla or something like this.
Yeah, I guess one had to first of all look what magnetometry options one has, and then also look into systematic effects maybe at these ranges. One thing you have to be careful probably is that, I mean, if you have a smaller absolute magnetic field, then your drifts are relatively larger, for example. Yeah, and I'm sure there's a bunch of other things you have to consider and then have to optimize there.
But maybe also your gradients get smaller and stuff. So just very speculative. I just thought about this.
For example, you still need a B0 field which you need to generate, and so you have a current supply which will have some fluctuations which might not all scale with absolute current or so. So I'm not sure if all of your gradients and all of your bad effects will also scale with going to lower fields. And your external field, like your gradients from the outside, for example, they also don't scale. I mean, maybe that is something that gets more interesting to look at now with these new beautiful magnetic shields where you have very, very low gradients from the outside. That might be interesting. I see Georg has unmuted himself, so maybe we'll ask Georg about his opinion. He's more of an shielding and magnetometry expert.
Yeah, I think if you convert, I mean, what we convert an electric field interaction into a frequency difference, and the frequency does not change. I mean, the frequency difference does not change if it's at 30 hertz or at 0 hertz. So you still have to measure with the same resolution a frequency difference or a phase difference if you consider a fixed precession time. So I think resolution-wise, you don't win anything. It's the same problem. What I would be worried about is to get the spins in and out. You still have to measure a precession angle that is something very small. And at DC, you have all kinds of disturbances. So I think that the fact that you can do an interference experiment at a small but finite frequency inside the experiment gives you such a large advantage, because you only care about, I mean, you care about fluctuations at your resonance frequency. And if you look at shielding factors and so on, that's much easier to get good conditions at a few hertz than at DC. So, and I mean, and I think, I mean, the big problem is how to get the spins in and out. They would depolarize at the smallest inhomogeneity that you would have somewhere on the way. So I don't see a practical. I mean, theoretically, it's I would say the same, but I don't see a practical solution how to do it at zero field. And a comment to zero field magnetometers. I don't know an accurate zero field magnetometer. There are very, very sensitive zero field magnetometers. But you would want to know that you are actually at zero field. And if you can use a precession frequency to measure a finite field, that's intrinsically significantly more accurate than typically the zero crossing of some resonance that you detect at zero field.
Yeah, and on the zero field magnetometry, you have also to remember that the true zero is typically only existing at one point or so. And so it sounds nice in principle, but to use it in practice is not so obvious.
That's a very interesting discussion, but I think we should close now the session. And thank you again, Diter. Yes, your lecture was remarkable, and it's nice that we have recorded it for later viewing. And so we reconvene at 2 p.m. Central Europe.